It doesn't take a day off.
Well, um, oh, it's here for the level of me. All right, so welcome to the engineering session. We do have it scheduled for the two presentations together and then question and answer, but we are going to take question and answers on the first presentation right after the first one. So we do have someone watching chat, so you can put a question in chat, or you can ask a question after they're finished. So I'll let them get started. All right, so my name's Hailey Carlyle,
I'm Jaquez, Dedeaux.
and we did the admissions and clearance processes here in U. So this is just a little history on Methodist. It opened in September of 1960 for all student business. It was known as Methodist College until 2006, and it serves approximately 2,300 students through different programs and class styles.
This is our problem statement. The admission and clearance process for incoming students should be easier to navigate and easier to understand, as well as provide adequate information and communication for each step in the process for students, parents, and faculty. Our hope is to help clear these obstacles and make the process easier for all those involved.
So some of our goals for this project were to make a process map of different departments so we can better understand them from start to finish. Develop a fishbone diagram so we can see the cause and effect of different problems and issues, and interview students and faculty to get different points of view and find solutions to those issues that were feasible. And here's some of the tools that we used.
Of course, we use lean tools to aim and eliminate the processes that are not valuable. For example, the repetitive emails sent by the offices. This is also used in many different industries. We also use the bottleneck analysis to help us figure out in each department where the bottlenecks are.
We also use DMAC, and DMAC is just an acronym that stands for defining, measuring, and analyzing and improving and controlling problems. Here's how we specifically used it.
First, there was we discussed the issues at hand, and we mapped out a project timeline and when we would meet up with departments to talk about the processes. We defined our measurable goals, such as meeting with, like I said, the involved departments and asking them a base set of questions. We also created a student survey, involved necessary non-primary departments, that still played a part in the processes, but wasn't one of the main 5 departments, and also document information.
So to measure our problems, we discussed the problems that we interviewed the students and they shared with us. We attended meetings with the involved departments. And aside from talking about the departmental problems, we talked about the student problems with the departments to get their feedback. And we created process maps for each department. And that'll be later in the slides and it'll be current state.
Next is analyze. We analyzed the bottlenecks in each department and what areas they were in. We got that we took the issues that students came to us with, and we basically was coming from the student perspective in this to compare the issues that we see, if there's like any overlap. The areas that we found there were issues were admissions, financial aid, student counts, office of advising, registrar's office, housing, and residence life and student body. The common issues that we did find were there were differences in systems. There was lack of communication. The MU portal was difficult to navigate. There were unresponsive students and parents, and there was a total lack of knowledge about the entire process.
So to help try and improve these issues, we met with software and system programmers, and we tried to pitch any ideas and receive feedback. We found new solutions that were actually achievable, and our goal was to redesign the portal to include a tracker tab or a non-static checklist. And we could also try and redesign student orientation in order to help incoming students and incoming parents better understand that process.
Lastly is control. We encourage students and faculty, parents to advocate for change with the processes and the MU portal, to communicate with involved departments and programmers to see what solutions are available in a short-term time.
So here's just a little backstory on some of the departments involved. The Office of Admissions handles applications and acceptance of incoming students. There are various types of students. So there's incoming freshmen, online students, graduate students, transfer students, international students. Some of the communication that the Office of Admissions uses is email, postal mail, and text messages if the student has opted in. And a communication trigger, so what triggers the communication to go to the student's missing documents.
Next is the financial aid office. They handle the scholarships and awards for various students. These students being these scholarships being third-party scholarships, university scholarships, grants, need-based scholarships, FAFSA and other federal loans. The communications used in the financial aid office is email and postal.
So the Office of Student Accounts provides financial management for students, and that includes the billing for tuition and other fees, processing payments for those tuition and fees. They maintain different adjustments on students' accounts, and they issue disbursements. So they also, in the clearance process, they clear students for class registration, and they use email and postal mail for communication.
Next is the advising. Advising assigns students an advisor, of course, which depends on the student major. They may assign a temporary advisor for the summer after getting accepted, or they could go another route depending on a volunteer, such as Dr. Bauer, who volunteers to be a temporary advisor over the summer and then stays with the student over the school year. Communication used in the advising office, there is no outbound communication unless from the advisor themselves. The advising department lists students' advisor on the MU portal.
So the Office of the Registrar provides information about enrollment. So that includes class schedules, the classes needed to graduate, transfer credits, and their communication that they use is just email.
Next is the housing, residence, life, and health. They determine where a student will reside if living on campus. A decision is made for the student freshman year. Students get to choose after that. This can reside at different residence halls based on earned credit hours. They put out programs to increase student morale and create a more welcoming and fun environment. They also make sure incoming students have necessary immunizations before coming onto campus. The communication used for the housing, residence, life, and health office is email.
So here are some of the process maps we were talking about. They're called current state. There's also a picture of the portal. So the 4 that are horizontal are the desktop, laptop version. And there's a clear difference when you look at the phone or mobile version. As you can see, all the tabs that we need are here and available already. And on the phone, you have to scroll over. And then the quick links button is actually kind of hidden, and most students don't realize that it's there.
This is the start of our process maps that we made for each department. Basically, how we created them is we went to every department, spoke with them, and we also looked at the process maps that we were shown on a static list to create these from start to end. This is just one example of, the student pays at the registrar's office and goes to that. Next is the admissions office. This one is obviously a longer one.
As you can see, there's a few more decisions in the bigger process maps. So like this one only has 3 main decisions. It's like, does the student have financial aid and things like that.
And here, there is
Here's the actual financial aid. So has the student had their information verified? Like if they're having FAFSA, has the government verified their information? And here are the proposed ideas that we came up with.
The first one, and probably the best one we came up with, was the non-static checkup list. The current checklists on Methodist portal, on the MU portal, are static lists that offer nothing besides the help of the list. It would be to use the capability of the MU portal to include lists that automatically check for yes and X for no. And we actually have an example of this. This is our example of how the static checklist would look on the MU portal. Say, it's pretty self-explanatory. Like if you don't have one thing, it's X'd out. If you have it, it's a checklist. Say you don't have it, that will be a link. You press on it, it will take you to where the document is in the MU portal that you need to complete, and etc. Yeah, that's just our example of that.
So the next thing we came up with was a tracker tab, and we figured we could add it on to the tabs that are already in the MU portal, and it would look better than this, but just an example is you would be able to click on admissions and financial aid and have a drop-down menu of what students do and do not have, and they can click on it and get a link to where they need to go. However, this is not feasible with the system that we already have. It'd be a lot of work and probably cost a lot more than Methodist can afford.
Our next idea was to redesign the student orientation. We came up with the idea to maybe move the orientation, move the orientation into over the summer. It will last about 2 or 3 days. The parents will come also. Student and parents will split so they can each learn on their own what they have to do. It would have student advisors for each department so that students can learn from their peers and feel more comfortable asking questions about the processes at Methodist. They can also have a Zoom orientation for those that are unable to attend in person. We spoke to the offices and about how this was an idea earlier, but there were issues because of international students having to come in.
So our conclusion was that the only true feasible idea would be the non-static checklist, because it can be doable with the systems that we already have. The tracker tab is too expensive and would not work out with the systems that we currently have. And orientation, the redesigned orientation, is up in the air because previously it didn't work out well, but with how much we've been using Zoom lately, it could work. It just depends on what the university would want to do with that. And then questions.
question.
Absolutely.
When we sat down and discussed the advising communications, I distinctly remembered we discussed that there's an automatic communications that's sent to the student and all advisors when the student is assigned, but that wasn't mentioned in your presentation.
I was putting the slide more from after they're assigned the advisor. So does that
Okay.
advisor personally send them a message?
Okay, we also discussed about 5 different templates for communication that are given to the advisors with the instructions of when and where to communicate with them.
Yes.
Okay, and then about the check sheets being static, the screenshot that you showed was not the one that we discussed about the electronic advising worksheet that shows every single degree program and whether it has been completed, not attempted, or is in progress. Why was that not shown?
That was just a small example that we were given to by assistant programmer Ryan Pretlow. So that same idea is applied in the the advising or the advising portion. So we were showing a little
Yeah, a
example.
small example of how the checklist would look in a way.
That's a little, but it was a little bit misleading as to the amount of information. We also discussed the GPA a generator where you can calculate your GPA and change it as many times as you want to you know, administer a GPA projection. We also discussed the different documentation that's available on the portal, but none of that was mentioned.
Well, this was more of just like we were saying, a small example of how the portal looks, and I think
Okay. It's
Yeah,
just a little bit misleading.
Yeah, our checklist was for the portal overall, not just for advising. So we focused more on what was on the portal for everything else. So that style of checklist could be used for more than just advising.
Okay, thank you very much.
You're welcome.
anyone else?
So what would be a big picture that you would want to do with the portal?
The big picture, I guess, would be the tracker or the checklist that we spoke of. Basically, there will be, could we pull up there, yeah, we'll go back to the one with the tab, yeah. Basically, we will put the tracker tab or the checklist here, and then it will show the list like we were talking about, this list here, where it would have each department, and you would click on them and it'll bring down a static checklist for each of the departments, showing what you do and do not have, like here. Like say this was under admissions, and say there was a document that you did not have. Say this is just a document and you do not have it, just forget about the credit hours, mainly just, and you do not have it. If you do not have it, you will click on the link to the information that you do not have, and it will come down and basically take you to where on the admissions page you need to be to complete that obstacle. But that's our main.
Yeah, that's our big idea. Our big plan is to use the tracker tab. But because that's not feasible currently, our smaller plan was the non-static checklist just on its own.
I have another question.
Absolutely.
Why was that deemed not feasible? Because that actually makes quite a bit of sense.
We spoke with different programmers, and just with the systems that we have now for the portal, it would be costly and it would take too much time, and some of the information isn't actually input into Genzibar for the portal to know if that information is there or not.
Okay, thank you.
You're welcome.
Anyone else?
Is there any other solutions that would cost less but would still get the same quality?
Not that we found. A lot of the solutions that we were thinking of were very expensive, such as like trying to switch to the same systems. Each office would be on the same system. That way, this wouldn't be as much of an issue with the lack of communication and things. But we found that was impossible considering, well, and not impossible, just not feasible because of the cost. So the best option that we could come up with was the static checklist.
Yeah.
It's not that expensive. It would be easier to create on the MU portal page. And that's the best way for students and faculty to be able to find what it is the student needs in order to complete their process, whether it's admissions, financial aid, etc.
Yeah, that checklist would help prevent a lack of communication, because students could go and see what they're missing without having to go to the office, or the offices could see what the student already has in without having to wait for the overnight delay or not get the information at all.
It'll also be easier for, like, if the faculty were trying to help a student find that information, they could just lead them to the page, the tracker page or the checkup page, and tell them where they need to go to complete what they have to do.
Now, if money wasn't the problem, how long would you think it would take to install this?
It really depends, from my point of view, I guess. It really depends on how welcoming everyone is to the new system. Because you can install it, but then how long is it going to take for everyone to understand it?
And then there's also, like, the having to input the data needed to be there. There also, like, there still has to be communication between the offices of, like, putting that data into the MU portal and onto the checklist. So if the document is there and it is completed, it needs to be inputted by the department that it is in there and completed, or it's not in there and completed. That's another thing.
But honestly, we didn't even talk about if money wasn't an option, because we were trying to find feasible solutions that we could do in a short-term time frame.
Any other questions? Or does that answer your question?
Yeah, I was also having my computer froze, so it was kind of coming in and out.
What did you not understand?
No, I understood it, but
Oh.
but my computer froze.
Okay. Does anyone else have any questions? That's it.
We'll have our next group come up, so they will start here shortly and we'll do the same. You gotta thank you for your presentation from one of the chatters. You gotta thank you for your presentation. From one of the
You're welcome.
participants from Dr. Carter.
Oh,
Thank you.
thanks for watching.
Good morning, everyone. I'm Aiden and this is my teammate Jaquez Lowe. And today we'll be presenting our capstone project on design of a wearable device for return to play for lower limb injuries. So lower limb injuries are extremely prevalent in sports, and this requires athletes to go through a return to play protocol when they want to go back to a game situation. Currently, return to play protocol is not based on any type of data collection, thus it has no baseline. So we developed a wearable device, as you can see on this picture here. That's a knee sleeve with a knee sensor. And we also developed analytics behind an app to derive the biomechanical performance. And all of this was based on data collection from the Methodist Motion Lab.
And a quick thank you as well to our advisors, Dr. Reddy, Dr. Bauer, and Dr. Foreman, who cannot be here because he's in occupational therapy. But we really appreciate your help this semester. So first, a table of contents. I mean, very basic. We're just going to go through background, problem statement, need statement, concept of operations, design requirements, the design, results, verification, validation, summary, and then future works. So a little bit of background, as Aiden said, lower extremity injuries are extremely prevalent in sports, especially in NCAA athletes. According to the NCAA, of the 4,800 athletes average that participate in NCAA sanctioned sport each year, over 90% of them will report some kind of injury throughout their 4-year career, and over 50% of these will be lower extremity injuries. Lower extremity injuries can include injuries to your ankle, knees, muscle tears, as well as ligament tears and sprains. So background for the return to play protocol. Return to play protocols require a trained professional who conducts a qualitative assessment, conduct it on the injured athlete, who has to perform a range of standard motions compared to their healthy side. For our standard motion, we conducted our motion on the vertical jump. As I said, they compare the compromised side to the healthy side, and there's no form of data collection from athlete to athlete or school to school. So there's no baseline nationwide. Another problem with this return to play protocol is it's conducted in a sterile environment. So it does not account for fatigue or endurance, as well as it does not emulate a game or practice atmosphere. So vertical jump methods. Why the vertical jump? It's a simple athletic motion that we found uses all muscles in your lower body, so it's the most comprehensive motion. As I said, it assesses the strength of your glutes, quads, hamstrings, and calves, and it demonstrates your athletic power, which is your athletic capability. So current methods of vertical jump test methods are chalk on the wall, vertec, video, and pressure and force plates. Chalk on the wall, as the name says, you jump and you mark the point to which your foot rose on the wall with a chalk. Vertec is shown here. This is the most common form, the most recognizable form from NBA or NFL combines. You mark the point to which your hand rose. Video can be analyzed through an app, and then pressure and force plates output ground reaction force, which then can be transmitted into a vertical jump height. None of these methods, as I said earlier, none of these methods are conducted in a game-like environment. They don't account for endurance or fatigue, and they are not adaptable to the individual. Another problem as well is, like the vertec shown here, some methods are easily manipulated because you can manipulate the vertec through shoulder extension, and then other methods like the pressure and force plate are extremely expensive and require high-speed equipment. So biomechanical sequence of the vertical jump, really when you bring it down into kind of your basic stuff. You get 6 basic steps. You get the neurosignals, muscle forces, knee flexion angle, ground reaction force, initial velocity, and then peak height. And we found that the last three steps here are the ones that are most commonly recognized or transmitted, commonly used. But the first 3 are not only what allows the vertical jump to take place, but what can be closely explained between individual to individual or athlete to athlete. And we found that these first 3 segments are also just currently overlooked by methods like the vertec or chalk on the wall. So events and phases of the vertical jump. So we have it broken down here into five phases. Standing, crouch, takeoff, peak height, and landing. Crouch obviously is when your knee angle is at the minimum, and from crouch you ascend upwards and accelerate upwards. You fly to peak and then fly to landing, and then after the jump once you land. So this is from data that we conducted in the motion lab. On the x-axis here we have frames in 1/100th of a second. On the x-axis we have z position in meters. So on these 3 lines, they show the height throughout the vertical jump of your anatomical position. In yellow at the bottom, we have the ankle in the Z position. In red, above that, we have knee in the Z position. And then above that, in the blue, we have hip in the Z position. So as you can see, as you begin to crouch, your hip lowers dramatically, your knee lowers a little bit, and your ankles remain stagnant. As you begin to accelerate upwards again, you rise, and once you take off, once you reach peak, your height is at its maximum. So these dotted lines, we segmented each section of the jump. So first would be standing, second would be crouch, the third one it would be takeoff, and then the fourth would be as you land again, and then in the middle there we have peak height. So it's important to note for our project, hip position velocity, which is what we're calling initial velocity, is when your hip reaches the point that it was whenever you were standing originally. So no two people are the
That's
same.
not good. There it is.
Dr. Fick, can you mute?
Dr. Fick, yeah, can you mute?
So this is also data collected from the motion lab. On the x-axis, we have x position in meters, and this is the amount that you sway forwards or backwards throughout your vertical jump. And the y-axis, we have z position in meters, which is obviously the amount that you raise off the ground. So one thing that's really unique here is that you can see kind of the fingerprint of two different athletes throughout the jump. Athlete 2 obviously has a significant more amount of x sway as compared to athlete 1, which has a much more linear knee pattern along the x-axis, as well as athlete 2 reaching about 0.4 meters higher throughout their jump. So as background summary, so return to play assessment requires training. It's currently very qualitative with simple metrics, conducted in a sterile gym / not game environments. It's not specific to an individual, as well as not accounting for endurance or fatigue. And there's no baseline from athlete to athlete, school to school, or division to division. So vertical jump biomechanics, vertical jump 4 phases, and we believe we can assess the musculoskeletal system by understanding biomechanics. So next up, our problem statement. Currently, and most of this is just a reiteration of what I said earlier, but currently there's no form of data collection for athletes to return to play. It's not quantitative. Pressure plate's very expensive. The most quantitative method is extremely expensive and requires high-speed equipment, to which very few people have access to. It requires training by a professional to be able to understand if you are healthy or not to return to play. It's not individual, or it's not specific to the individual athlete. It does not assess their musculoskeletal or their biomechanical patterns. And as I said earlier, it's not conducted in game situations. It's conducted in a sterile gym environment, as well as everything just kind of being a one-time test.
So this will lead us into our needs statement, where we need a wearable device that will make the return to play process quantitative, will make it available to all athletes, not just strictly professionals who those have access to athletic trainers. We want to make it tailored to the individual athlete, specific to their biomechanical and musculoskeletal system. We want it to be conducted in game-like situations on the field of reports and not just in a sterile environment. We want it to account for endurance and fatigue, as these are two main factors that lead to re-injury and injury in general. So for our concept of operations is first and foremost, we want to be able to provide a baseline for biomechanical data. We want to be able to compare data from an athlete before they're injured to an after they're injured. And this will be able to account for individual athletes and their differing musculoskeletal systems. So to do this, we want to create a wearable knee sensor with analytics on a smartphone and tablet, as you can see in this picture here. So it can be worn outside the lab, and it will make it more accessible to people who may not have access to pressure plates and motion labs. We also need to create an algorithm to convert knee angle to usable metrics. So we want to be able to gain deeper insight into athletic movement rather than just looking at the height of a vertical jump. And we also need to make these outputs comprehensive so the average person can understand them and use them. So for the biomechanics measured for the vertical jump, by using a knee angle sensor, we'll be collecting direct data for knee angle during the jump. And this will then in turn give us knee angle rate and knee angle speed. The metrics that this will output is vertical height, hang time, initial velocity, and ground reaction force. This is the functional flow of our design. So we're starting with a wearable knee sensor and a knee sleeve, and this will in turn transmit data from the knee brace to a smartphone. So the phone has to be able to receive and store this data. It needs to be able to calculate performance metrics. It needs to be able to display these performance measurements and metrics. And lastly, we'll have an interactive user face for the user. So here you can see the GUI of what our app would look like. So on the first screen here, you would press start and start by connecting your sensor through Bluetooth to the phone. From there, you would start collecting data, and it would give you these simple outputs. On this screen, you can see knee angle speed, initial velocity, and estimated jump height. And if you're interested in learning more and taking a deeper look into the jump, you can click into it, and it will give you graphics and more in-depth metrics. So our mission requirements is that this system will measure knee angle flexion as well as knee angle friction rate with an accuracy of plus or minus 2 degrees. The sensor will not impede any biomechanics, so an athlete won't have any trouble wearing this. So it's going to be very light and be a very small volume. It will be a reasonable cost for small schools and athletes as to make it very accessible to everyone. It will operate for more than 120 minutes, and it will be able to operate in all types of weather conditions, so it can be used in outdoor athletics. Next is our design requirements. It'll be able to perform calculations very quickly in 0.1 seconds. It will have an on and off switch for the wearable sensor. It will also have an on and off indicator. It will have a battery status indicator as well as a low battery alert. And it will be able to update the information to the smartphone app in real time. So looking more into the algorithm behind the app that develops metrics, these are the basic equations that we're using to get the metrics. So we collected vertical jump data in the motion lab in order to understand the vertical jump and to actually break down these mechanics. And this is how we form these equations. We're applying our understandings of these metrics into the algorithm. So the theoretical equation is that jump height is equal to initial velocity squared, all divided by 2 times g. And from the motion lab, we found an equation that jump height is a function of initial velocity. We're also able to find equations that show initial velocity is a function of knee angle acceleration. And lastly, we were able to find that knee acceleration is the second derivative of knee angle over time. So here showing our first equation is showing how jump height is a function of initial velocity. So on the x-axis here, you can see initial velocity measured in meters per second. And on the y-axis here, you can see jump height measured in meters. And this had a relation of r squared of 0.887. And this is an equation that, a linear relationship that we use when developing the jump height from the knee bend sensor. In order to understand what initial velocity is from the jump, we are able to use knee acceleration. So here on the x-axis, you can see knee acceleration, which is measured in meters per second squared. And on the y-axis, you can see initial velocity, which is measured in meters per second. And this has an r squared value of 0.84. So next, we actually developed a knee angle sleeve with a knee angle sensor. So here you can see the bend sensor attached on a hinge that has a small battery attached that provides the power. And on the right side, you can see some pictures of what our app would look like. So the next test that we did was a verification test, which we ran in the Methodist motion lab, where we compared the motion lab data to the data that we got from the knee angle sensor. So as you can see here, the mean of this data is negative 0.31 degrees. So this shows that the knee bend sensor doesn't have a lot of error and can be easily calibrated. The next test that we ran was validation testing of the jump metrics. So as you can see on this graph here, you can see on the x-axis is jump height error, and on the y-axis is count. So for this, we were able to compare motion lab jump height to the knee sensor estimated jump height. And from that, we were able to understand that the algorithm estimates jump height within 5 centimeters of error, which can also be easily calibrated. So overall, our results, when looking and breaking down the vertical jump biomechanics, we're able to see correlations between jump height and hip velocity at takeoff, which is what we refer to as initial velocity. We also saw correlations between hip velocity and the knee angle acceleration. So our knee sensor data matches the motion lab data on average by negative 0.31 degrees, and our algorithm estimates jump height within 5 centimeters of error. So this leads us to future work, which is really a budding industry as these new sensors are becoming more accessible and cheaper for everyone. So this could be applied to both the left and the right knee. It can be used for other biomechanical movements besides the vertical jump that include lunging or running. It can be used in injury prevention. So we'll be able to collect data on athletes as they practice and be able to get a better understanding of when they're more likely to be injured. It can have an improved knee sleeve and improved attachment methods. And lastly, in sports, it can have athletic performance improvement. And when you take this out of the sport environment and apply it to other real world applications, you can use this in the military or in workplace situations where they're also going through similar types of biomechanical movements.
No question. I guess the question slide this. Yeah. I'm just. So, does anyone have any questions?
What type of models did you look at to figure out the app?
To figure out the app, we broke down. Yeah, if you go to
Oh, you want me to sorry.
yeah,
Which one?
you go to the one with the one. Yeah, like this. So we specifically went to the motion lab and we collected a bunch of different jumps. And from this, we were able to plot different points on a graph, as you can see here. So these are all of our real jumps that we did in the lab. So specific to the first point, you can see it was roughly 2.2 meters per second initial velocity. And that jump resulted with 0.35 meters in jump height. So we use these linear regression equations in order to plug in the numbers in the app.
Hello, Dr. Foreman's indeed here. Great job.
Thank you.
We talked a lot about, we went back and forth a lot about the limitations of using one joint angle and one activity as like a predictor of return to play, right? So can you guys maybe talk about that a little bit and like the assumptions that go into using knee angle and vertical jump to say like you're ready to go back to play soccer?
Sure. So return to play protocol in general is kind of already a proxy of what you're assuming an athlete would do. And the idea of this isn't to necessarily replace return to regular, like current return to play protocol, but the idea is to be able to create a baseline for athletes. So by using something like this for vertical jump, we can gain a better understanding of how athletes are biomechanically moving and what's going on in their musculoskeletal system, and be able to compare it to themselves as well as to other athletes. So it's not to say that this athlete, if they score a certain number, is good to go, but it's to gain a better understanding of how they're moving post-injury.
Yeah, and like Aiden said, so really the interpretation of this originally was to create it off of the athlete's individualized baseline pre-injury, similar to how the NCAA does concussion tests currently. So we wouldn't necessarily be looking at whether or not they perform, how they perform after with just pure raw data. We would be looking at how they perform afterwards when compared to their previous tests that were conducted prior to injury. And as long as we meet a certain threshold, then we would say then you are returned to clear, or you're cleared to play.
Perfect. It'd be like a tool in the toolbox, right? Amongst a bunch of other things, and simple, easy to put on, spits out data fast. Yeah, I think that's great. Good job.
Thank you. Anyone else?
Could this be used during a contact sport like football?
Yes, but this would have, I mean, it would have to be, obviously this is our first prototype. So eventually down the road, I think, as Aiden said, we could put that into future works with an improved knee sensor sleeve that would be resistant to impact, similar to how NFL teams are using concussion-prone helmets now with sensors inside of them.
Would it only record, would you only do one knee at a time, or would it be where you could do two at the same time?
Again, this was our first prototype. That would be in future works for left and right knee. For this current sensor, you can only do it one knee at a time because it only bends with the way that your left knee would bend. So if you put on your right knee, it'd be backwards. But in future works, we could develop a system that works on both knees or works on both knees simultaneously.
I think it's also important to note that when doing a vertical jump, it's accurate enough to just assess one side at a time, assume that the other side is following suit. So for this type of product, just doing it on one knee didn't give us a big enough error. That was the problem.
Great, thank you.
Oh, stop sharing my bad. I didn't see it.
Great, well, thank everyone. Dr. Coleman, just great job in chat, see what I'll chat.
Dr. Women have a message for you guys. He's waiting for the center.
So Dr. Fick said to Jaquez and Hailey, the things from the student facing business process. I get it right. I'm on the committee and yeah, you can see them. And so Dr. Patton, Dr. O'Neill, Dr. Robbins. So thank everybody for coming. This hopefully it's still recording. So if you want to go back and visit this later, it'll be posted on the CRC Symposium website. And again, thank everybody for joining us today, and thank you all for the presentations. Good job. Enjoy the rest of the day.
Thank you guys.